Look closely at the delicate fins on this 3D printed metal turbine impeller. Producing geometries this precise requires absolute perfection at the microscopic level. In powder bed fusion, that perfection starts with spreading thin, sequential layers of metal powder over a build plate before the laser fires, spaces or voids within the spread layer. Those microscopic void spaces survive the melting process. They translate directly into physical discontinuities, reducing the density and mechanical strength of the final product. Predicting the structural integrity of a printed part is impossible unless you can first accurately predict the dynamic, mechanical behavior of the raw powder. For decades, the additive manufacturing industry has relied on the Hall or Carney flow rate tests to benchmark powder flow. The mechanism is highly traditional. You measure the exact time it takes for a set volume of powder to fall through a calibrated orifice. The flaw in this method is gravity. It measures the powder in a completely static, unconfined state, relying only on the material's own weight to initiate flow. Simply pouring powder into a static funnel introduces incidental aeration. The results become heavily dependent on how carefully the operator loads the sample. Modern manufacturing environments aren't gentle funnels. Inside the machine, powders face variable feed rates, high shear forces, and are mechanically compacted. Bridging the gap between testing and actual production requires a shift to dynamic powder rheometry. Rather than waiting for powder to fall passively, a rheometer forces a mechanical geometry directly through the powder bed to capture its active mechanical resistance. Relying on static funnel tests for highly dynamic, pressurized manufacturing processes creates a foundational engineering mismatch. To accurately measure dynamic flow, we use a specific hardware geometry, a Hawk-Mars rheometer equipped with a specialized vane rotor. The rotor features 4 distinctively twisted blades designed to plunge directly into the sample cup. The rheometer does not push the rotor straight down. It drives the instrument through the powder bed in a precise helical trajectory. This path is controlled by isolating 2 distinct vectors, the machine's downward axial speed and its rotational speed. Combining these 2 controlled variables produces a resultant vector, the tip speed of the rotor blade, along with a strictly defined operating angle. For standard data collection, these parameters are calibrated to maintain a constant 5-degree helix angle as the rotor moves. By locking this geometry in place, engineers can subject the powder to exact, repeatable stress states, entirely removing human operator bias from the testing cycle. Bulk powders physically retain their handling history. The way they are scooped, poured, or vibrated during loading significantly alters their starting density. To establish a valid baseline, this history must be erased using an initial conditioning cycle. The rotor moves downward while rotating clockwise, allowing the twisted edges of the blades to gently slice through the material and release trapped air. This slicing motion yields a uniform, low-stress packing state, known as the conditioned bulk density. With the baseline set, the rheometer shifts into test cycle mode by reversing to an anti-clockwise downward plunge. In reverse, the flat faces of the blades heavily compress and shear the particles to simulate actual manufacturing loads. Isolating the gentle conditioning baseline from the aggressive testing stroke allows the rheometer to measure true material properties without interference from arbitrary loading errors. As the rotor shears its way down through the test sample, the system sensors capture 2 distinct forms of physical resistance. The first metric is torque, which measures the powder's friction against the rotational motion of the blades. The second is normal force, capturing the upward structural resistance against the rotor's downward axial plunge. This is the central equation used to synthesize those raw forces into a singular metric known as flow energy. The system integrates the combined torque and normal force precisely over the exact vertical distance the rotor travels during testing. Because the math explicitly accounts for the radius of the sample cup and the 5-degree helix angle, the output remains perfectly standardized across different testing batches. By executing this calculation, abstract physical resistance becomes a quantifiable unit of energy. Engineers secure a hard numerical value for flowability under load. A single energy reading is only a snapshot. Predictive power requires a multi-step protocol of alternating test and conditioning cycles, as detailed in this procedural chart. The first phase of the protocol executes 7 identical consecutive testing cycles. This data generates the stability index, or SI. It is calculated by dividing the flow energy of the 7th test by the baseline energy of the first test. If the SI ratio diverges significantly from 1, the data proves the powder physically degrades, fractures, or agglomerates when subjected to repeated mechanical stress. We also extract critical data from the upward recovery strokes of cycles 6 and 7 to determine specific energy, or SE. Specific energy tracks the force to gently lift unconfined powder, revealing how rough particle textures physically interlock and hook together without heavy compression. The stability index dictates how a powder survives the long-term grind of a feed hopper, while specific energy dictates how smoothly that same powder behaves when lightly spread across a build plate. The final sequence of the measurement protocol deliberately tests kinetic sensitivity by altering the machine's speed. Across the last 4 cycles, the rotor's downward tip speed is sequentially reduced from 100 millimeters per second down to 70, 50, and finally 25. This generates the flow rate index, calculated by dividing the flow energy at the slowest speed by the energy at the highest speed. The flow rate index quantifies the material's exact sensitivity to changing mechanical velocities, a parameter that is critical for calibrating industrial discharge rates. Failing to account for this kinetic sensitivity, a minor feed rate reduction causes the bulk material to suddenly arch, bridging and jamming the production line. By tracking the stability index, specific energy, and flow rate index together, engineers construct a comprehensive mathematical fingerprint of the powder's behavior. Retiring static funnels in favor of dynamic rheometry allows advanced manufacturing facilities to replace trial-and-error physical testing with rigorously calculated predictive engineering.